Yebo, Jumbo, Hotep. Hello guys, Akwaba. I am coming back to talk to you again about dynamical systems. I am Marcelin Ninidabo, PhD on control systems. I am a consultant in engineering in the industry, and I am an independent researcher. So I have done some previous videos on open loop first order systems, meaning having a direct excitation as input and to check the output. So that was done for the first order systems. For second order systems, I have done other videos showing that it is possible to compute a time response or any performance related to time for the response of our dynamical system of second order. What does it mean? It means that if you consider the three cases of the second order systems with a damping ratio that is different to 0, you have one case that is underdamped, meaning that the damping ratio is less than 1, greater than 0, less than 1, okay? And then for that cases, I have shown that it is possible to compute specifically for any given value of damping ratio and any given natural pulsation, the temporal performances in terms of time response, for example, at 95%, 90%, the rise time between 5 and 95%, etc. And then the same thing for a system that is critically damped and overdamped. Okay, the case for which the damping ratio is equal to 0 is not studied here. It's just a simple expression that we are going to show you. So in this part, as I have talked about the first ones, meaning that the over damped system, okay, and the underdamped system, I will be presenting in this video a critically damped system, meaning that with the damping ratio equals to 1. So very important for your information, during all these presentation, this one and the others, I will not be talking about transfer functions and the system in other domains. No, I will just consider the temporal domain. And then also, I will just work on stable systems. I will not study unstable systems. So if you are ready, we can start. If you consider actually a second order system, this is presented as this one here. I have done these comments for the other videos. If you want to go deeper, you will refer to the other ones for this presentation, but I will just give quickly the first basis. So here B over A0 can be identified to B over omega n squared, because here, as you can see, you don't have a coefficient here. So in order to remove the coefficient here, you should divide by this expression. For this expression A1 over A0, it is corresponding to 2c divided by omega n, because if you divide all this by omega n squared, you will simplify by the omega n, and then it will remain another one here. And then the A2 over A0, you will have 1 over omega n squared here, okay? So now for an autonomous system, if I talk about an autonomous system, we consider B equal as 0 here, equals 0 here. And then it means that the system doesn't have an input. And then the initial condition is different. The initial condition of the variable s of t is different. Here you have the input e, here is the output, and it's the first derivative and second derivatives. This is why second derivative, this is why we talk about a second order ordinary differential equation, ODE. So from here, what we do is that we have these expressions I was saying for an autonomous system. You have the initial condition that is different from 0, and another function of time that is here. This function of time can be divided in two parts. The first part, it is a sinus of a given expression, The second part is an exponential, and then you divide by the square root of 1 minus c squared. Look at here. For an underdamped system, what you have is that the system is living in a trigonometric world, okay? Trigonometric circular world. So this circular world, the dynamic of this system is pushed to the equilibrium by this exponential function, okay? Here, when the system is critically damped, you have this expression here. You have the origin here. Okay? And then what you have here is that the system is lying on a line, a temporal line, and you have always this function, this exponential function. That is the same with this one, because it's just the times that has changed, the position of the time variable that has changed. This is td, that is the departure instant, minus t, that's what we have here. And here we have the opposite, t minus td. This is why you have the minus here, okay? But anyway, these expressions are the same. If you check the overdamped, you have actually this expression, and the system is living in a hyperbolic world, because here you have the hyperbolic sinus, the arc cotangent hyperbolic arc cotangent of this expression. So for the underdamped and overdamped systems, the expressions, the solutions are quite the same, I can say, except for the functions, that trigonometric functions that we use for the first one here in the circular world, and for the second one in the hyperbolic world. Also, the expression under the root is different because of the sign of the xi, okay? In the first case, xi is less than 1, so you have 1 minus xi squared, okay? And then this expression is positive, of course, so the square root is well defined. Here is the same. If you check xi is greater than 1, if you put a xi square, you will have it is greater than 1 square and equal to 1, and then the square root is well defined. And then the particular case is that for which we consider xi equals to 0, this will yield to this expression that we can consider for the oscillating pure oscillators, okay? No damping factor, and then the system will continue to oscillate if you let it start, okay? So it's very important to understand that from now I will just consider this expression, okay, and I will be working on this expression, okay, for the next simulations, to show you that it is possible from this expression to compute the time response, the temporal performances, as I was saying. Next, so here you have just the characterization from the previous laws, how they behave in reality in a plane according versus time. So you have the step response here versus time, and you have their behaviors here. You can see these oscillations. For this one, the blue one, it is because the value of the damping ratio is closer to 1. For the yellow one, it is more closer, and the difference between the green one and this magenta, it is because here for the green one, I make a difference in the pulsation, but their xi, their damping ratio is quite the same, okay? So you can have damping ratio the same, but when the omega n, the pulsation is different, the time response is varying, okay? Here what we have is for the damping ratio greater or equal to 1, and then you have this kind of responses. Recall that these are only for autonomous systems. But you can do the same even for systems for which what you have is that the initial condition is greater than the equilibrium point, for example, for a step response, and you can go from this part to reach this one in the sense of differential equations. If you check this in the sense of transfer functions, for example, you know that the initial condition is always equal to 0, and then you will not have it at any time this kind of representation. Okay? For a step response, I mean. Let's go again. These are face portraits that I want to show to you very quickly because present in the other videos. So you have the oscillation can be represented like this. It looks like you start in a circle, a given point of a circle, and then as time goes by, you will converge to the center of the circle, like this way, okay? This is what you see here on the dashed lines. For the continuous line, it is because the sorry, the damping ratio that you have is here is getting closer and closer to 1, and this is why when you leave a given point with an initial condition that is not 0, you will move and you will be pushed by the exponential function to converge to the equilibrium. Let's go for the next one. This is a critically damped, and then you start here. The system is living on a line. Just a comment here. I have separated because here normally it's an imaginary axis. I don't use the imaginary notation. I just take the real part and then the imaginary part without considering that it is imaginary, and I put it here. I say that the system is living in a circular world with a trigonometry that is circular, of course. And I was saying here the system lives on a line and it is pushed by an exponential function, always the same exponential function. So you start here and then you move to the equilibrium. Okay? It is exactly this. Look at this one, it is quite a line, and this one also, it is quite a line. As you can see, this, it depends on where you start. Sometimes where you start somewhere, you are pushed directly to the equilibrium. Okay, no curves, like in the case of underdamped systems. So here what we have is overdamped systems, and then you consider here a hyperbolic space, hyperbolic world, okay, where you have here in some sense the first part of the solution of the characteristic equation, and then here is the second part. I wanted to see this presentation. This is why for the underdamped equations, underdamped system, I don't use the imaginary axis. I just use this, okay? So for all these presentations that you have seen, if we go back to the expression of these solutions of our differential equation according to the damping ratio, what I can tell you is that I have introduced an only single time constant for second order dynamical systems that is equal to 1 over xi omega n that you can see here. So any given dynamical system of second order that you consider, I have introduced only one time constant that is equal to 1 over xi omega n. And then based on this introduction of this new vision, I have derived some formulas that you can see here for to reach the time response or the time constant of your system. Okay, if you take alpha r equals 1, you find here the time constant of my system, and this is a percentage of the initial condition at which you can find the time constant of your system according to the damping ratio that you can have here, right? So this is for underdamped systems, okay? For example, these formulas they are defined for the damping ratio of 0.7. And then if you want to compute the time response at 2% of the initial condition, you should come here and use this formula, okay? For 5%, for 10%, for 20%. Recall that if you have a step with initial conditions that are 0, what you do is just complement to 100%, meaning 100 minus 2%, and then you will be able to compute the time response for a damping ratio of 0.7 at 98% of the equilibrium or of the final value of your step response or your initial response. It is equal to 3.109 divided by the natural pulsation. And these are done for the time rising time, okay? And the percentages that you can see here are always for the step response used as a complement of 100%. We will say rise time here will be from 2 to 98%. Rise time here will be from 5 to 95%. Rise time here from 10 to 90%. Here from 20 to 80%. All these percentage given here are related to autonomous systems. Okay, let's go again. So this one have been presented also in a previous video for the damping ratios that are greater than 1, and then you can observe the percentages at which for any given damping ratio you can find their time constant. And then this time constant, as I introduced and defined, is equal to the double of the relative time constants. Okay? So now we are going to talk about this formula. We are going to talk about these expressions because this has been treated for systems with just the damping ratio that are greater than 1. And the example for the formulas that I have considered are here. This is the time response at 2%, and then we have here the time response that is equal, the damping ratio considered here is equal to 1.65. This is what I have written here. I just avoid to put a point here. So it is corresponding to 1.65, and if you want to find the time constant, you will be using here you will be finding the time constant of your system at 90% here, okay? 90% of the initial value, okay? So now let's go for this expression here, okay? We consider a given system with a damping ratio that is equal to 1. And then for this damping ratio that is equal to 1, where can I derive the time constant? I can derive it at 73.58% of the initial condition, or for the step response at the complement of 100% of this, okay? It should be 42 here, and then if you take a 5, you have 1, 1, 6, okay, 26 point something here, okay, 0.42, 26.42. And then the time response that we'll be having is given by this formula, okay? The rising time for a damping ratio of 1 also can be computed as this, and then we can have these expressions to compute them always according to omega n. So now, all these studies, as I already said, you can find them in my next book. So it is coming very soon. So prepare yourself to buy this book because I give many details inside that can be very helpful for you as a teacher, as a student, as a lover of engineering. And this will be very useful for you for your studies. It's a new vision. It's a new paradigm that generates new methods that will help to solve these kind of questions. So now let's go for simulations. For simulations, what we have here, Okay, let's consider now this example here. So as I explain here, I have two things, okay? The laws that I have presented you here. These laws, I put them in the MATLAB program, okay, the MATLAB code, and then particularly this one that I will be using for this case of a system that is critically damped, okay? And then I also use I also use a Simulink here of a second order model. And then for this Simulink, if we look at inside, what we will be seeing is the differential equations that we have at the beginning, right? With the initial conditions that are given here. For example, this is for the velocity, the derivative of the variable, and then here is the variable itself. So how does it work? When I start, I give two values. The damping ratio that is fixed at 1 for this example. The other damping ratios, the other examples for the other damping ratios have been given in another video, so I will be not giving them here. And then when I start, what I do for this omega n, that is natural pulsation, what I do is I use a random value, okay? And then I give the other one. And then from these ones, I derive all the coefficients that you have here in the Simulink. The goal is to launch the simulation from Simulink. Simulink will give me a trajectory, a response trajectory, okay, or an initial response if you want, or a response of an autonomous system, meaning that the entrance of the system is equal to 0. And then from there, I define initial conditions for my autonomous system. If I am using it, when K is equal, Ke is equal to 0, this is Ke, the amplitude of the step. Here are the initial conditions for my step system. I put them all to 0 to avoid, to make the things simpler. This is a time where I define my simulation time duration and steps. This is the place where I select the initial condition according to the value of the amplitude of input. And then here I launch first this simulation. And then from here, what I do, I compute the corresponding output according to that equation I show you. And then from here, I plot them together, the result of the simulation on Simulink and the result of my computation from the model here. And afterward, I can derive the values of the time responses and performance and temporal performances. So note that with this simulation, we just know the value of the damping ratio here. This is the only thing that we know, and then we know also the value of B2. But the omega n we ignore, we don't know it. It is generated randomly. So how will we be able to calculate this value? This is what we're gonna see also. So now let's go for simulations. I am rushing because of time. I don't want to do a very long video. Look at this. If we evaluate what we are going to have, the result is coming very soon. All right, so what we have here is that we have a response here. So recall that to have the time response, so this is a step response that we have. So we have to go and take the complement at 100% of the percentage that we need. It is here 73.58. Let's go for that. Let's check 73.58 minus 100. 26.42. So let's go at our figure, make it a little bigger. Okay, and then we check now what we are going to have. 26.42, we take a point from here, and then what we have, 26, we say 0.42. So we can consider this, and our time constant is around 0.1828. Let's go and find it. You can see it is exactly the same that we have computed from the theory. Okay, it means that if you have a system like this, to find its position, you just come at 26.2042 of the final value. Okay. What I could do is I could also change the different values such that value of B such that it won't be at 1. If I do that for the equilibrium, I would be obliged to always come back and compute the percentage, for example, 26.42% of, if the equilibrium is at 0.92, I will compute this percentage times 0.92. Okay, and once I get that result, I can come and find it on the line, etc., etc. Okay, so let's go for the time response, for example, let's say at 95%. Okay, at 95%. Why 95%? Because this value at 5 here has been defined for autonomous systems. So you have to use the complement at 100%. Let's go. So we go at 95%. And then let's try to get it. Yes, we can consider this is good, and we have the time response at 95%. That is equal to 0.86.72. 86.72. You see here, it is only 3 over 10,000. That is remaining here to have the good value compared to what we have here. If you stop only at two numbers, two digits, okay, you have 0.87 here, and here also you have 0.787. It could be the same. So now you can see that it is the same result. So the formula is working, and then you have the simulation is giving something correspondent. The formulas are giving corresponding results to the results of simulation. We can check the time, the rise time, for example, between 95 and 95%. So let me come here, and then here I try to define a given point at 5%. Okay, at 5%, what we are going to have is this. So we have 0.065. Let's now compute the rise time between these two values and check if we will have this value or not. The computation is given by 0.8672 minus 0.065, and then we have 0.8022, and then this value, you see that there is only four, the difference is 4 between these two. Okay, so you can see that the formula is correct. The formula is correct for the computation. So now, how to compute, how to derive omega n? We can derive omega n by doing so. We have the tau. Okay. The expression of tau is 1 over, so tau that we have is here. Okay, this is a time constant for a damping ratio that is equal to 1. And then this expression is equal to 1 over omega n. It means that if we need the omega n, we just call it om1. We say it is equal. We keep the 1 that we had at the beginning. Okay. And then we divide by tau. This is the value. And then if we go and ask for the omega n that has been generated randomly, you can see that it is the same. Okay? I can position myself and check for the rise time that I have computed, for example, and then come to the rise time and show you how to compute this value. For example, if I take this, okay, this is the rise time between 5 and 95% in our case. Where is it? It is here. Omega n equals this constant 4 point. So if I call it Om2, I say it is equal to, I will put 4.386, 4.386 that I divide by this value. And then you can see that the omega n is again the same. Okay, I can derive omega n for any given time response that I have from here, right? So this can be applied for this one here. So you have the omega n, okay, it is given here. You have the b, the static gain is equal here. You have also the xi that is equal to 1. So you can change the omega n and try to see what you will be having like as a result. So I won't do an autonomous, the calculation for an autonomous system. In my simulations to have the autonomous system, what you can notice is just I put the amplitude of the input at 0 and as the initial condition is equal to 1 here. If I execute the program, I will just evaluate this. Okay, and by doing so, what I will be having, okay, is as a result the different time responses that I normally have. Okay, and then you can see that we can go again and compute all the things that I need. So the complementary 200, okay, no. The complement to 200, it will be, just to show you quickly, 100 minus 73.58. 100 minus 73.58, 26.42%. This would be for the complement, but as I have here an autonomous system, I just take 73.58. 0.3374, this is a tau. Okay, let's go. So you have the result is here, and it is quite the same that we have here, right? And then from there, we can derive the time response at 2%. Let's check it here. Time response at 2%. Let's go to 2%. And then for 2%, okay, what we are going to have here, this is our 2%. 1.9688, 1.9685. It's quite the same, okay? So guys, thank you very much for watching this video. So you understand then now. This video has been, I present in this video the possibility to compute the time response and the performance of time at any given percentage, okay, of your initial condition for an autonomous system or of your final value for a step, an initial response. I give you the formulas, the details of the formulas for any given damping ratio that you can find. I am able to give you the formulas to compute the time responses, okay? For this video, I did it for a damping ratio that is equal to 1. There are other videos before this that I invite you to check, and this video is closing all the 3 videos that have treated, in which I have treated the case for which the damping ratio is less than 1, damping ratio is strictly greater than 1, and finally, damping ratio is equal to 1. These are the 3 cases that I have treated in this series of video, and for all of them, just understand and notice that it is possible to compute the time response. Okay? So anyway, thank you very much for watching this video. I hope that you have enjoyed. And please don't forget that this book is coming very soon for both versions that are English and French. This is the French versions I am presenting here. It is only written dynamical systems, new vision, new paradigm, new methods for characterization, identification, design, and control. So please support our job, support my job by joining the channel, by sharing these videos, by liking, and then also by commenting if you can. Okay. And then from now, I say to you goodbye. I hope we will be able to exchange again very soon. So thank you again and see you soon.